11. In this lecture, we will introduce a problem called vertex cover. And then we will use dynamic program to solve the vertex cover problem on rooted trees. So let's start. So for vertex cover, we assume that we have an input graph, let's call it G, which is an undirected graph. We can somehow imagine that the vertices of G represents the road junctions and the edges are rows. And now consider placing a guard at the road junctions. So if we place a guard at some vertex V, then all the rows incident to the vertex V will be protected. The target here is we want to place the guards so that all the rows are protected. And if possible, we want to use the minimum number of guards. So how to do that? So let's see an example. So we have an input graph like this. It has 6 vertices and 6 edges. Now, if we place the guards here as shown, then we will find out that this road is protected, this road is protected, this road is protected, right? This road is protected by this one, and these 2 rows are protected by this one. So we will see that all the rows here will be protected. And then we are using 4 guards. But for the same graph, we can see that we actually need 3 guards, and it is already enough. So if you look at this edge, it is protected by this one. These 2 edges are protected by this one. This edge is protected by this one. These 2 edges are protected by this one. So again, all the edges are still protected. And then we are using a fewer number of guards. Indeed, 3 guards is the best possible for this problem in this particular input. The reason is that if you look at this edge, and this edge, so these 3 edges, they do not share any vertices. So what does that mean? It means that if we want to protect this edge, and this edge at the same time, we have to place a guard in one of these 2 vertices. We have to place a guard in one of these 2 vertices, and also a guard in one of these 2 vertices. So that means that 3 guards must be needed, at least. So in that case, we cannot do anything better than 3 guards, and the particular scenario that we show here is already an optimal placement of the guards. Now this problem is called the vertex cover problem. So we place guard at the vertex so that all the edges, all the rows are covered. Now in general, this problem is super hard. So far, nobody has found any polynomial time algorithm to solve this problem. But it doesn't mean that we cannot solve this problem in polynomial time. So it's not equivalent. It is just saying that nobody has got a polynomial time algorithm. So it is still open whether a polynomial time algorithm exists or not. Now in this lecture, we will restrict the input graph to be a tree. And suddenly the problem becomes much simpler. And this problem will then be able to solve in linear time. And again, this is an example of dp, and then we are going to use dp to compute the minimum number of guards first, and then after that we will store extra information that allows us to do backtracking so that we can obtain the optimal placement of the guards. Now since the input graph is a tree, so we are now using T to represent the input graph rather than G in general. To simplify the discussion, we will assume that the tree is a rooted tree. So don't worry if the input is an unrooted tree. We just pick any arbitrary vertex and set it as the root. Now, to solve this problem by dp, we are going to use the standard mode of thinking. So we are going to think backward. So let's ask this question. So suppose that we know the best way to place guards in the subtree of each child of the root. So we want to determine how to place guards in the whole tree. But we don't have information of how to place guards in the whole tree yet, but instead we have solutions. We have somehow knowledge of how to do the best in a smaller subproblem. So we have the subtree of each child, and then suppose that we know how to place the guards for that one. Now, can we get the best way to place guards in the whole tree? So for instance, let's see this example. So we have a tree. Suppose that we know, oh, this is the best placement. Okay, so we need one guard to cover all the edges in this subtree, and also one guard to cover all the edges in this subtree. Can we make use of this information? One guard here in each of the subtree, so that we can compute that, oh, the best way for this case is 3. Can it be done? Well, let's also see another example. Now in this example, this part we will need one guard, and this subtree we also need one guard. But however, this looks like the previous problem. It is a root connecting to two subtrees. The left side needs one guard, the right side needs one guard. However, the best solution for this example is to place only 2 guards, rather than the best solution in this example, we will need to place 3 guards. So what does that mean? It means that just knowing the best number in each of the subtree of the children will not be enough. Okay, so just knowing the best way to place guards in the subtree does not work. So what actually was the problem? So the problem here is that when we place guards optimally at the root in the subtree, so a guard could be placed at the root, or it could be not placed at the root. So in this example, when we perform the best way to place the guards for this subtree, we cannot place a guard at the root of this subtree. But for the other examples, we can place a guard here and here as well, right? So that we still can have the optimal number of guards in the subtree. So this actually makes a huge difference, whether the optimal way to place guard in the subtree, whether we are placing a guard at the root or not. Now to solve this problem, then what we are going to do here is, instead of just storing the best way, the minimum number of guards to place in the subtree, so let's call it the best value, we also store another thing. So we want to store the minimum number of guards to place in the subtree so that all the edges are covered. But, this is important, but we require that we must place a guard at the root of the subtree. So in this case, let us call this value best 1. So 1 means that we must place a guard at the root of the subtree. Now suddenly, storing best and best 1 will be enough to compute whatever value that we want. So in particular, let's see how this can be done. Suppose that we have a vertex V, and this vertex V has children C1, C2, C3, and so on and so forth. Now best 1 represent what? Best 1 of V represent what? It represents I want to cover all the edges in the subtree rooted at this V, but requiring that the root, which is the V, has to place a guard. Now best 1 of V can be computed easily by using the previously computed values. It is because we are now placing one guard at V, so it is a 1. But then we will need to cover all the, so by placing a guard at the vertex of V, all the V to children edge are all covered. VC1 is covered, V to C2 is covered, and so on and so forth. So what we just need to care is, how are the edges in the subtree rooted at C1? How are the edges in the subtree rooted at C2 and so on are covered? So this will be easily done because we know that this value is already computed. This is going to be the best way to cover all the edges in the subtree rooted at C1, which is best of C1. and then best of C2, and so on and so forth. So best of V requiring that we must place a guard at the root can be computed based on the previously computed values like this. Now, how about the case in general? So best of V here, we do not require that the root node must place a guard. So that means that the best way can come from one of the following. Maybe we are placing a guard at the root of this tree, which is the node V, or we may not be placing a guard at this root node V. Now, if we must place a guard at V, then in that case we have gotten this value. This is best one of V, which is computed already, right? Now, if we do not place a guard at the root node V, then what does that mean? It means that to cover all the edges in the subtree, not just the subtree of edges in C1 is covered, we also need to cover the edge between V and C1. So in that case, the root node C1 here of the subtree rooted at C1, it has to place a guard. So we will need best one of C1. And also best one of C2 for the same reason. And also best one of C3, and so on and so forth. So the first sum here represents the case that what is the best that we can do if we do not place a guard at the root node V. And the following, this line, it tells us that what is the best way to do if we must place a guard at the root node V. By comparing these two values, the minimum will be the best that we can hope for. So let us see an example of how it works. Okay, so this is an example run. So we are solving this problem by solving the smaller subtree first, and then the larger subtree later, and finally the whole tree. So if you take a look of this node, this is a single node, okay? So single node also represents a tree, right? But it does not have any edge. Now, because it doesn't have any edge, so the best way to cover the subtree rooted at this node, so we do not count this edge, so we count the subtree, okay? But there is no edge. So we actually do not need to place any guard. So best is equal to 0. But on the other hand, best 1 requires us that to find the best way to place guards here, but we must have a guard placed at the root. So in that case, although there is no edge, but we require a guard must be placed here, so best of 1 is equal to 1. So again, this is the same situation. So best is 0, best 1 is 1, and also this one, best is 0, best 1 is 1. So actually, these are the so-called boundary cases. Now, how about the next one? So let's consider a larger subtree. Now, this subtree, we have this node here. Now, for this node, if we want to compute best 1, then we put a guard here. And then for this part, then we can do the best whatever way that we have. So the best 1 can be computed as 1 plus the best here, which is 0. 1 plus 0 is 1. So best 1 is computed as 1. Now to get the best value, we need to consider two cases. The case where we do not place a guard here, so we want to have best 1 from here, so which is 1. Or we place a guard here, and then in that case, we can relax a little bit. We can choose the best here. Both of them will give us the same value of 1. So in that case, we can write down best is equal to 1. Now, how about this? Okay, how about this? Now, if for best 1 is we are placing a guard here. So in order to cover everything, so we place a guard here. These two edges are already done. So we find the best way here and the best way here. So best 1 is equal to 1 plus 0 plus 0, which is equal to 1. And the best, we need to consider two cases. One is already done, best 1 is equal to 1. The other is we do not put a guard here. And if we do not put a guard here, then we must place a guard here. So we will look for the value of best 1. We must place a guard here, so we must look for the value of best 1. So in that case, if we do not place a guard here, we will need 2 guards to cover all the edges. But then the minimum comes from this one. So best 1 is 1, so then best is also equal to 1. Now this is best is equal to 1, best 1 is equal to 1. So how about this one? So let's take a look of a larger one. Now for this one, best one is we place a guard here plus whatever that we can do the best here. So 1 plus 1 is equal to 2. So best one is equal to 2. And how about the best? The best, we will compare the case where we do not place a guard here as well. So if we do not place a guard here, then we must be placing a guard here. And then placing a guard here covers this edge. So we are going to look at best one for this subtree. Best one for this subtree is 1. So in that case, the best for this one is the minimum of 1 and 2. So it is equal to 1. And finally, for this one, so let's forget about the next page. Let's do this mentally. So how about the value of best one? So best one for this node is easy. So it is 1 plus the best for this one plus the best of this one, so which is equal to 3. Best one for this one is 3. How about the best case? The best case, we are going to consider the situation where we do not place a guard here as well. If we do not place a guard here, we look at the best one value and the best one value. And again, they sum up to 3. So we have best and best one both equal to 3 in this case. So this is what we can conclude. Now for the other example, so let's get familiar of what we are doing. So this is another graph. So again, best and best one are computed. Based on best and best one, we can compute this case for the larger subtree. Now, when a node has all the information of the subtrees done, then we can come up with the value here. Now the difference here is that this time best 2 at best is equal to 2, because when we consider the case that we do not place a guard here, we can choose best 1 and best 1, which is equal to 1 plus 1, which is equal to 2. So indeed, best here actually can be obtained by doing best 1 here and best 1 here. Okay, so this is the example run. So the actual implementation to find out all these values, we can do something like this. We can traverse the tree by depth first search, and the traversal of this tree by depth first search takes linear time. So we spend linear time. And then along the way that we are doing this traversal, we will compute the minimum number of guards to place in the subtree of V. So we will find the best value of V and also the best one value of V at the time when V is last visited. So in particular, so what we are going to do here, so we are going to do a traversal, depth first search traversal. So we will first find out the value of this one. When we go back, we find out the value of this one, and then we continue the traversal, and then we will hit this one, so we compute this value. We will hit this one, compute this value. And when we go back, we will find out this node, and then by this time that this is visited, all the subtree information are known. So we now know the value of this one. When we have the value of this one, we go back, we have the value of this one. And at this moment, we have the value of this subtree, and we have the value of this subtree, which allows us to compute the value of the root node. So in that case, by doing a depth first search traversal, we will be able to compute the corresponding best and best one value one by one at the time when the node is last visited. Okay. So if we analyze the time, then we will find out that the time to spend at a certain vertex V is equal to 1. Yeah, we are going to spend at least 1 unit of time visiting there, plus the number of children of V. The reason is that we will need to look at each child of V and look at the best value and best one value. So it is proportional to the number of children of V. Now this is the time that's spent on a particular vertex. So the total time will be total number of vertices, because 1 from each vertex, and plus the total number of edges, because the total number of children of every node adds up to the number of edges. Because it is a tree, there are n vertices and also order n edges. So the total time that we are spending in the computation of this best and best value is order n, together with the depth first search time, order n, so the total time is order n. So this allows us to compute the minimum number of glass needed to cover the edges of the tree. Now finally, how do we find the placement of glass? It is actually quite easy. So we are doing the backtracking. So this is what we have obtained so far after the traversal. Now when we do backtracking, we are asking, oh, what should we do for this root node? We see that best is the same as best 1. So it is good to place a guard here because it is best 1 is equal to 3. So one of the optimal solution will be placing a guard at the root node. So we are placing a guard here because best 1 is also the same value as best. And next, let's determine what to do here and what to do here. On the left hand side, again, the best is the same as best of 1. So best 1 gives us one of the optimal value. So in that case, let's place a guard here. But on the other hand, on the right hand side, best 1 is 2, best is equal to 1. It tells us that in order to get the optimal placement, we should not place a guard here, because placing a guard here, we will need 2. But if we do not place a guard here, we may be able to place 1. Okay, actually the best way is to place 1. And similarly, we continue the process. Best is equal to 0, best 1 is 1, so we are not placing a guard here. But on the other hand, this side, best 1 is also the same as best, so we are placing a guard here. So in the end, this is what we are doing. So in the end, for this particular example, we are going to place the guard at these 3 locations. Now, in fact, for the vertex cover problem on rooted trees, there is a different algorithm which is simpler that allows us to solve the problem in also linear time. This method is called greedy method, and we will talk about this later after we have finished our discussion on dynamic programming. However, the dynamic programming approach can help us to solve a more general setting. So what does that mean? Okay, so here, imagine that we are not counting the number of glass that we need. But then, when we place a card at different vertex, there will be different cost. So maybe some vertex represent some expensive place, which is like a dangerous place. So in that case, you need to pay more for the guard. And some vertex, it represents some safer and nicer place. So in that case, you need to pay less for the guard. So we want to place guards the same so that all roads are protected. But we want to minimize the total cost of placing the guards. So how can this be done? So in that case, this is called the weighted vertex cover on rooted trees. So let me leave this as an exercise for you. So it is actually very, very simple. Just perhaps one minor modification to this. Yeah, this is the recurrence that we have. Just one very minor modification of this one allows us to compute the minimum cost placement. Okay, so that's all for this lecture. Thank you.